Hi, my name is Joseph Johnny. I'm with Johnson & Johnson Center for Device Innovation. This is the session for 3D printing fine and microscale features. I'm joined today by Yasmin from the Fraunhofer Research Institute, Bru from Medtronic, and James from Empire. Welcome, everyone. I think we're going to take a moment and just go around the horn and give everyone a chance to introduce themselves. Yasmin, would you go first?
Yes. So my name is Yasmin Selbe. I work at the Fraunhofer Institute for Laser Technology in Aachen, Germany. And I'm team leader in process development for laser powder bed fusion. So we work with metal 3D printing. And there we can print microscale as well. And we call it micro LPBF. And I think we can discuss something today about it.
Bru, would you go next?
Yes, thank you. Hi, I'm Bru Jacobs with Medtronic. I'm a principal scientist in our biologics research and development group. And we've been working on understanding the intersection between product development and commercial viability for biologic 3D printed structures. We also look at fine and unique structures to facilitate bone growth and cellular healing. I'm looking forward to the talk today. Thank you for having me.
And James?
Yeah, hi everyone. I'm James Grimm, and I work for a wonderful company called Empire Group. We are a service bureau out of Southern Massachusetts, and we specialize in full product development. We've got our term that we refer to it as 360-degree product development. We work with our customers on a variety of projects from all different industries, from medical, military, automotive, and consumer products. And we also have a wide range of technologies available in 3D printing, CNC machining, urethane casting, mold making. The list kind of goes on. And we also have a big a group of design and manufacturing engineers on staff as well to help with product development.
Thank you for that. So the very first question I think that we need to all align around is, what is microscale additive manufacturing? How do you define a fine feature? And to some extent, this is process dependent. So I'm going to go around the horn and let everyone talk about their individual processes as well as what they define as microscale. Go for it. Let's start with Yasmin.
So I think some of you may know laser powder bed fusion, and there we work with a normal laser beam diameter of 80 microns and can print, normal parts as everyone had probably in their hand already. And we have a new process we call micro laser powder bed fusion, and there we use a very fine laser beam of 25 micron and less, fine powders and everything, so we can create a dimensional accuracy or dimensional resolution of 30 microns around, and very fine surface quality. So 30 micron might be minimum size of our micro process. That's how we define micro.
Bru, could you comment a little bit on polymers?
Right, thanks. So we are attempting to print with biodegradable polymers, some of which have a viscosity that makes it difficult to maintain microstructure once those polymers are extruded. We like to be down around 30 microns, maybe to 50, in order to get the appropriate, attraction for any cellular attachment we would be looking at with our final product. As we look at micro technology and microscale printing, it's about how do we drive better integration with our host as an implantable device. So we have a little bit of room to vary what we can look at as far as the range for microstructures, but we also want to trade off repeatability and precision with how small we can get for some of the fine features.
And Bru, what's the process that's associated with those materials?
So we're looking at a couple of different processes, some of which we're developing in-house, some of which we partner with other research institutes. So some of them are off the shelf. They're your larger known companies, but we're also looking at how we develop our own printers and processes to get to the structures that we want to see. So there's a lot of IP behind it that I'll hold on to for now.
Sure. James, could you comment on the photopolymers?
Yeah, absolutely. So the technology that Empire uses for microprinting is known as BMF, Boston Microfabrication. And this is a projection SLA system, and it can produce parts down to resolutions of 2 microns. And you can get hole sizes and thin walls of about 5 times that. So that 10 micron range for small holes and thin walls, and the accuracy is equal to that, right? So we see it's very capable of holding accuracies of 40 microns is extremely achievable, and once we analyze a part and construct a build pattern for it for repeatability, we can dial in those accuracies even tighter than that.
So I think it's fair to say, just from everyone on the panel here, that really how small you get is very much process dependent, process specific, as well as what's the application that you're looking for. I think we're all agreed that once you get under the 50 micron scale, you're definitely crossing over into microscale printing. But it sounds like at that point, really, you're just limited by your imagination, your money, and the process that's available to you. Do you guys have any other aspects maybe that you would want to draw attention to as far as what should be an input to your decision making when you're trying to print something that's extremely small?
Yeah, I think a good place to think about it, right, is if your part is a micro part, or if you're trying to capture micro features. And so, we have a variety of customers that approach us with parts that are, on the micro scale themselves, right? So the entire part is less than 2 millimeters in size. And we also have customers that come to us with parts that are maybe, 100 millimeters across, and that have just some features that need that extreme tolerance and resolution. So there's a big difference in those types of parts. So I think, the cost of a larger part that has high resolution, high accuracy, and micro features is pretty high compared to some of these just micro parts in general.
Let's talk about just all the infrastructure around 3D printing these really, really small parts. Yasmin, could you talk a little bit just about some of the differences that people have to take into consideration when they're looking at their powder and the materials that are going into the actual 3D printer?
Yes. So if you want to print micro laser powder bed fusion, you would use very fine powder. So a normal laser powder bed fusion, we have metal powders of 15 to 53 microns, 60 microns. And we would use that powder for layer thicknesses of 30, 50, 100 microns. So this is the bigger process. And if we talk about micro laser powder bed fusion, we have the small beam size I already mentioned, and we use the finest powder. We have less than 10 microns or maximum 10 microns. So we can realize a layer thickness of maximum 10 microns and create these fine features by pulsing the laser. So we have very fine, small melt pools. But you have to consider that if you use these fine powders, it's very challenge to deposit the powder for the powder bed. So you really have to adapt the deposition of the powder, and this is the challenge we are facing at the moment. And we found the solution by ultra sync the deposition of the powder deposition. And this is how we can deposit the fine powder, and then realize the very fine melt pools and then the micro scale parts.
What do you guys do as far as post-processing?
Yeah, that's a challenge. I think James is facing even more. So if you have these fine features, you really have to handle it very carefully. And if you want to cut it from the base plate, yeah, you have to face these challenges, and these are very different from normal laser powder bed fusion.
Could you comment on photopolymers, James?
Yeah, absolutely. Yeah, that you're totally correct. There's a number of challenges that come from post-processing, and in our world too, where we're providing these parts as a service to our customers. We have to deliver these parts too. So, I think there's a funny little story that has happened already where I think the engineers who design a lot of these micro parts get used to seeing their parts on a gigantic screen. And we delivered the parts, and they accused us of shipping them an empty box. It certainly wasn't empty. And so, packaging these parts is a challenge alongside of post-processing. And there's a lot of things that we are, learning as we go here, because so much of this technology is extremely cutting edge. So we've had to adapt new practices for handling the parts. We have special containers for shipping them. We have a variety of new tools for quality control and inspection, which is another whole nother thing when it comes to micro parts. Measuring micro parts for quality inspection is a huge challenge and a very time-consuming process. So we're learning as we go and getting better at it every day.
You brought up something that I think that's really, really interesting, which is the quality checks, and that kind of ties into the next set of questions that we wanted to discuss, which is, when you're talking about differentiating between something that might be a prototype versus something that might be designed for commercialization and manufacturing. Bru, maybe you could comment a little bit just in terms of things that you have to consider as far as testing these microscale 3D prints.
Yeah, right. So you're going to want to have a robust VAR plan for your micro parts, for any parts that you want to take into commercial pipeline, of course. So it is a big difference between a prototype, a one-off, maybe a single print that you're going to do for a job versus something that's repeatable. So we would be looking at the accuracy of the part and the ability to match that drawing, the specs of what we intended to make with what our output was. As you get into the fine features, that becomes that much more difficult. So yes, the analytics and the testing behind what we're actually creating becomes almost a secondary project to ensure that we're doing enough, but it doesn't burden the process of getting to commercialization.
So maybe you guys could comment just as a group about what might be feasible, or maybe give some examples from your own experiences about things that might be feasible at the prototyping stage, but kind of fall or wash out when it comes time to actual manufacturing and commercialization.
I'll start, sure.
Okay.
At the prototype stage, right, we're willing to experiment. I mean, we experiment on anything from the parameters on our machines to the materials that are available for it. We can even go as far as help a customer develop a material, a photopolymer material that is, for their specific case, and build the parameter set to run that part. When you get into production, we're seeing this more and more where if you're going to go to production with a 3D printed part, we are asking that we spec most of these parameters, orientation, material, which system was used, what was the resolution, as many of these parameters that will affect the quality of the build, spec those on the drawings, just like you would for a machined component. And then that makes everybody accountable for making sure that the reliability and traceability is there for a production style job. When it comes to inspection, that's a whole nother thing that needs to be agreed upon between the supplier and the customer. And that's a little bit of an unexplored area for us when it comes to 3D printed micro parts, just because it's such a new process. I'm sure the rest of the panel has some comments there too.
Yeah, if I might add, so from our side, we are on the research point. So we make the process development and we investigate the influence of process parameters on our materials. And we have quite very different materials, even if it's metal. So we print with gold or even molybdenum, tungsten, besides the standardized powder materials you can use with LPBF anyways. So if we make the process development with our small size features, our test features, we can compare with each other. Then maybe we find the right process parameter, but then we go into the real part with the complex geometries. We even have to adapt the process again. And then we have one part which fits all the requirements and has the right material properties even as well. Then the next step is if the customer wants to have more of them, then there are more on the platform. And then the complete thermal history and then the pausing times vary a lot compared to the one part we printed. So then again, we have to check everything if the material properties still fit or if we have to adapt the process parameters. So we are on the research side, not very, not on the production side, and we see a lot of difficulties. But I think if you have the right machines and one part you really want to print in serial production, for example, then you can face these challenges.
Yeah, and what we're thinking of is that process iteration can be burdensome to some companies, right? Without a larger infrastructure to be able to support that replicate iteration to get to those features that you need. So that's something that we work through to make that viable in a sense of the cost and time and the resources that go into that. And so we have a team that can do that, but it also takes away from some of the other things that we could be working on. So as we're looking at how we develop the process, the luxury of working for a large company is that we're always thinking about what it takes to get through any regulatory hurdles that we may have. Is this going to be a 510K type of product for, say, something like a cardiovascular stent or a insertable cervical spinal cage? So it varies as much as the intent and the output, as well as that process, which kind of gets us to the barriers of having more commercially viable 3D printed structures and microstructures. So it is that process iteration that becomes key to developing a 3D printed structure for commercialization.
So it sounds like at a higher level, when you're talking with your company or your org, there's definitely a sense that you're going to have to lower your expectations as far as what your quality or throughput is going to be compared to your standard regular 3D printed parts. Would you guys all agree with that?
I think we're in, well, I'll speak from Empire's perspective, right?
Mm-hmm.
So the projection SLA microprinting is very cutting edge, right? Just released in the United States this year. We were one of the first companies to adopt this technology and start learning it. And it's a walk before run approach for us. I would say we're kind of just starting to jog with it. So yeah, whether you need to lower your expectations or not, I think you need to be prepared to approach every project as a development project. And I think Bru, you said this really well, right? You got to kind of learn your process, develop your process, and develop your parts alongside of it. So yeah, it's certainly a walk before running stage that we're in right now.
Okay, well, did you guys have any other comments about the Microscale 3D printing, particularly with respect to process, particularly with respect to feature size, or things to consider when you're comparing prototyping versus manufacturing?
Yeah, Joseph, you touched briefly on the infrastructure and the 3D printing industry. And I think all of us at each level would say that as that infrastructure is put into place, we'll see more development in not only micro printed structures, but actually commercially viable structures. So to all of the companies that are working on the printers, the new process that can be used, there's smaller scale nozzles and extruders for bioprinting, the smaller micro particle powders that Yasmin mentioned. I would just commend all of you and say that, you're laying the groundwork for us to do something amazing in 3D printing. So it's going to be a great future as that infrastructure builds out.
All right. On that note, let's take some questions from the audience.